here we go with a tutorial, or rather two tutorials, on capacitance. So let's get started. What is a capacitance? I'm going to say the same thing as I said with resistors. You are a capacitor. We're rather a lot today. It's probably this jumper that I'm wearing actually. So I'm something like 300 to 500 picofarads. Obviously a picofarad being 1,000th of a nanofarad. Or it may just be that the meter's not very good. It's quite a cheap meter. Quite a good one, but quite a cheap one. So okay, so you are a capacitor. Other than that, what is a capacitor? Well, a capacitor is two plates, conductive plates, separated in the middle by an insulator. Now that insulator could be earth, could be air, could be plastic. In fact, most often modern dielectrics are plastic because of a little thing called dielectric constant, which we'll get onto shortly. So capacitors then are quite easy to make. Well, small ones are. So let's make one. Let's make a capacitor. Here we have two things you will probably have in your kitchen. We've got good old aluminium foil, and we've got some food wrap, otherwise known sometimes as cling film, saran wrap, you name it. So first of all we want 2 bits of foil, and that's something we can put our meter on. Throw the junk away. So there we have 2 bits of foil. Now we want a piece of food wrap, and the piece of food wrap wants to be around twice the size of a piece of foil. Because we're going to roll this piece of foil up in a minute, we want to insulate both sides. So here's a piece of food wrap. Just tear that off. It's more difficult than it looks. It's fighting for its life, folks. Okay. So here's a wonderful piece of food wrap. And we will place the foil so that the tab is sticking out. And then we'll fold the full food wrap up behind it, and hopefully. So here we are. After we're all rolled up and carefully insulated, and we will put our probes on it. And what have we got? We've got something like 1.2, 1.3 nanofarads. That's not bad. So now if we take the same thing, I'm going to squash it. I'm going to really push this down tight to try and get all of the air out of it and try and get the 2 plates as close as possible to each other through the roll. So now I've done that, what have we got? Okay, let's have a look. So now I've done that, lo and behold, I have something like 3 or 4 nanofarads. So we've discovered that a capacitor is simply 2 metal plates, or conductive plates, separated by an insulator which we call a dielectric. And what a capacitor actually does is it stores electrical charge, and it does this by means of setting up an electrical potential field within the dielectric. Now a capacitor is kind of like a rechargeable battery, except that rechargeable batteries can only deliver a small amount of power per unit time. If you were to try and suck out 90 amps from a tiny little AA battery that was rechargeable, it wouldn't do it. However, if you were to try and suck out 90 amps from a little capacitor, it would probably quite happily do it, but only for a short period of time because there's not that much charge in it. And what this means is that large capacitors, especially ones charged up to reasonably high voltages, are very dangerous things because they can store an awful lot of power. Now the unit for measure of capacitance is called the farad, and because Mr. Faraday was playing around with milking buckets, big 8-gallon copper ones, and he was measuring capacitance between them by stacking one bucket inside another, it's actually very large. So What affects the value of a capacitor? Well, the area of the overlap of the two plates. If you were to have, say, a plate that was a square mile and another plate that overlapped it that was only 10 centimetres square, then the big plate, the fact that it's absolutely huge, wouldn't have much of an effect. What matters is the overlapping area. The distance between the two plates. The material that's used as a dielectric, separating the plates. And the reason for this is that different material have different dielectrical constants. Now, what do we mean by this? Well, a material can only take so much electric charge inside it. Some materials can take a lot of electrical charge, and we call those high dielectric constant materials. A lot of plastics, for example, have a dielectric constant of about 4, compared to air, which has a dielectric constant of about 1. And the dielectric constant is measured relative to the vacuum. So the vacuum has a dielectric constant of 1, and we symbolise that usually with E0. So to calculate the actual capacitance of this capacitor we have there on the left of our drawing, the actual formula is that capacitance C equals the dielectric constant times the free space constant, which incidentally is 8.84 times 10 to the minus 12, very small number, multiplied by the area of the plate that overlaps, and divided by the distance between. So as you can see, as the area gets larger, the capacitance grows larger. As the distance between the plates grows smaller, the capacitance gets larger. As the dielectric constant increases, the capacitance gets larger. Now, the dielectric choice doesn't just affect the value of the capacitor. Of course, it does this through the dielectric constant. And here's a table of some quite common things that are and have been used as dielectrics in the past. For example, air. Now, you might think it odd to use air as a dielectric, but with a variable capacitor, a lot of them work by simply having a set of sliding plates, and you adjust the overlap between the plates. And these use air. And going down the whole list, you'll see that there's a bunch of plastics like neoprene, nylon. There's also some materials like paper and paraffin wax, and glasses and ceramics. Now, there's a lot of capacitors that are made out of ceramics. But this dielectric constant isn't the only thing that is a factor when you consider a dielectric. You also have to consider the working voltage and the leakage current. And every material has a breakdown voltage in terms of megavolts per millimetre, and beyond that the material will break down. Usually it goes sort of sparks and smoke and all that sort of thing, and it carbonises and then current flows. It becomes a conductor. And with dielectric thickness often measured at a micron or less, this suddenly becomes very significant. Now, polystyrene is a very good dielectric, but it has a breakdown figure of 19.7 megavolts or so per millimetre. Now, 19.7 million volts sounds like a lot. However, at a micron thickness, then that becomes a mere 19.7 volts. So you wouldn't want to put, say, 24 volts across that capacitor, and in fact, you'd probably only use it as a 12 volt capacitor. Also, every insulator conducts ever so slightly, which was something that I mentioned back in the resistance tutorial. And this conduction is the major factor that causes leakage current, because a perfect capacitor would, when disconnected, retain its charge indefinitely. However, in practice, there is a current that flows between the plates, which evens everything up, and it dissipates that charge with time. In addition, to make really large capacitors of a reasonable size, an extremely thin dielectric must normally be used, and this has got bad implications for leakage current and tolerancing. Often the dielectric is a metal oxide that's just a few nanometers thick, and they grate chemically on the foil electrodes. And those capacitors are normally the aluminium can capacitors, the electrolytic capacitors, most of which are polarised and have to be connected in the circuit the right way round. If you connect them the wrong way round, they slowly become not a capacitor. Now, to make very accurate capacitors that are used in critical timing circuits, polystyrene is a superb dielectric, and it's often used. And although 1% tolerance can be achieved, the expense due to the difficulty of using polystyrene as a dielectric makes it hard to justify using these capacitors. Polystyrene is an awful material to handle industrially. It's very difficult to make so that it's got a consistent dielectric value, and it's very difficult to make in thin layers. So it's a bit of a nightmare material, really. So why are capacitors so useful, and why do we use them? Well, one thing is timing. Now, there's a thing called an RC or a CR time constant. Sometimes it's just called the time constant. And if we connect a resistor and a capacitor in a circuit, as the one on the right there, when we put the switch over to the charge portion of the circuit, then the voltage obeys the curve on the left-hand portion of the graph next to it, the blue curve, and slowly charges up to 12 volts. Then if we flip the switch over to discharge, and in that case it obeys the curve on the right hand side of the graph, and the voltage drops slowly down to 0 volts. Now when I say slowly, what do I mean? Well, there is this thing called the time constant, and basically you take the capacitance and multiply it by the resistance. And if you look along the bottom, that scale is in time constants. So at time 1t you've got 63% of the final voltage, time 5t you've got 100% of the final voltage, and so on. Now as an example, for our circuit that I've shown there, t equals 0.0000022, which is 220 nanofarads, times 2,400,000, which is 2.4 meg resistor. And that gives you 0.528 seconds. So referring back to the graph, at 0.528 seconds, the voltage will have gone from 0 to 7.56 volts. And if you have a circuit that can detect that particular voltage, 7.56 volts, you can make something switch at 0.528 seconds. Or you can count multiples of 0.528 seconds, and after those multiples have gone, then you can do something else that requires a longer time period. And these characteristics are very useful when you want to make a timer, or when specific actions have to happen a certain time after the equipment is turned on. Some types of oscillator use them to provide a time base. A popular one that's well known to hobbyists is the 555 timer circuits. And also they're used in filters to filter out undesirably high or undesirably low frequencies. And the next characteristic that's useful at DC or near DC levels is to use it for blocking voltages. A capacitor is obviously a break in the circuit. You've got an insulator between the two sides, and this means that you can use one to insulate two circuits that carry different DC voltages without having any current flow other than obviously the leakage current between the circuits. A signal, however, as we will see in the next tutorial, can often still pass. So this is one way of passing a signal from one piece of equipment to another when you don't really know what the voltage of the second piece of equipment is, or whether it's accurately the same as yours, or whether it's totally different. And often such a capacitor is called a coupling capacitor, and it's used between bits of equipment, between stages of an amplifier, and so on and so forth. Anywhere where you don't want the DC on one side to be the same as the DC on the other. So if you look at the two diagrams below, the first one's rather a bad one, because as soon as you connect that wire between the two circuits, it's going to pass an awful lot of current, and it will smoke and melt. Maybe even explode if it's a very small wire. Good luck. The second example, however, we've got a 100 nanofarad 50 volt capacitor in there, and that's absolutely no problem. But if we were to have specified, say, a 15 or 16 volt capacitor in there instead of the 50 volt capacitor, then over a period of time it would probably break down, and suddenly it would start conducting, and then you've got the smoking and melting situation again, and possibly a fire on your hands. This is one reason why it's very, very, very important to specify capacitors that are 1.5 times roughly the voltage of the circuit. Is a good safety factor. So, as you can see, there are an awful lot of different types of capacitor. There's ceramic ones, there's plastic ones, there's little tantalum bead ones, there's great big aluminium ones, there's tiny surface mount ones. You can get some surface mount capacitors now which are less than a millimetre in every dimension. It's like a grain of sand. So not only have you nowadays got to worry about what type of capacitor it is, what type of dielectric it is, what voltage it is, and what the value is, you've also got to worry about the physical size. Will the thing fit on your board? Cue a little story. A boss of mine once decided that he was going to build a prototype circuit, and he looked in our company-wide parts list, which had a big list of all the things we normally buy, and he wanted a 2 microfarad capacitor. And he saw this line in the parts list that said, under voltage it said 6.3, and under capacitance it said 2.2, and he thought, well, that's near enough. And without looking at anything else, he decided, right, I'm going to order one of these. And he didn't really care too much about the size because he was building a prototype. However, it wasn't until about a week later a van arrived, and what he got was a rather large power factor correction capacitor which took up the entire inside of the van. This sort of thing, as you can see at the left there, is designed for electrical substations, and thereby hangs a bit of a tale. You need to be sure that what you order is actually what you're getting, and it always seems to be capacitors that go wrong. So be very, very careful when you order capacitors to make sure that you get the right one. And that's all for this tutorial, and I'll see you in the next one when we're going to be talking about signals, AC values and filters. Thank you very much.